Okay, welcome to this talk. We're going to present making a headless Android device and the lessons we learned in doing so. My name is Johan Herland. I work for Cisco Systems in Oslo, or Lysaker, doing video conferencing equipment. Previously, I worked for Opera Software, and I've also done some work open source, mostly on the Git project. Yeah.
My name is Patricia Aas. I currently work for Vivaldi Technologies. We make the Vivaldi browser. I brought some stuff over there, so be sure to take some with you. Before that, I worked at Cisco Systems as well. And before that, I also worked at Opera Software, making the original Opera browser, which I hope everybody used. So this is the outline of the talk. First of all, why? And we'll look into that, both why us and why you. And then we'll dig into the architecture, the types of devices you can make, problems around composition, a little bit about Chromium, and a lot about the lessons that we've learned. Okay, so first of all, why us? We have worked on or next to or tried out a whole various amount of models in this space, what kinds of devices and how the architecture could be. And some of those projects have shipped, some of those projects have never been shipped, some of them died in demo stage. And so we have a lot of experience around this area. And what you will see, and with the lessons I will tell you, are hard-learned lessons. Generally, we can tell you that any kinds of things that we point out that you shouldn't do, we have done. So basically, the space that we're looking at is, and oftentimes where you will find yourself in a traditional embedded Linux space where you've been shipping embedded Linux devices for a long time and you have a lot of experience in this area, and we expect a lot of you do. But we're getting to the point where if you're wanting to make a next generation device and you're looking to get a new chip, you're going to have problems maybe getting an embedded Linux distribution for that chip. They're going to give you Android. And this is basically exploring what kind of solutions lie in this space. The problem is if you're in the Android side or in the embedded Linux side, they're pretty well known spaces, but if you're trying to explore the area in between, it's a little bit difficult. And the title of the talk had the word headless in it, but headless will mean two different things in this talk. First, it's the idea of having a headless Android bot, so basically chopping the head off the Android robot, so taking away parts of Android, and also headless in the way that having no display. So we'll look into both of those.
So, when you start a project in this embedded Linux or Android space, there are some important questions that you need to consider. In short, what do you already have, or where do you start? Do you have an existing code base that you're bringing into this new device? What kind of board support package do you get from your system on chip? And what third-party dependencies are you dependent on? What other code do you need to get running on the system? Next, of course, another important aspect is what kind of device are you making? Does it have a display or not? Do you run a single-purpose, single application, or do you run multiple apps? And how much custom hardware do you have? So before we sort of consider those questions in detail, we need to look at what the platform itself looks like, what kind of alternatives you have there. So we're going to dive into that. So, just to consider the main differences between Android and embedded Linux first. When you get an Android BSP, you get the whole package. You get a full Java ecosystem with apps on top. You get a very complete graphics infrastructure. It's currently supported by a lot of modern system on chips. And when you dig down into the details, at the bottom you have pretty much a regular Linux kernel, but with some Android features turned on. It used to be that Android had a fairly big patch set on the kernel itself, but these days that has been upstream, so now you can just flip a few config switches in the kernel and you get the Android features. What will become more important in following slides is the libc used, and I'll talk more about that later. Whereas on the embedded Linux side, you have a lot of stable or well-known components. It's not, when you start doing embedded Linux, it's not like you get a full package with everything available like you get in Android. It's more of a mix and match where you pull in the components you need to build a system to support your application. You can write your application in C or C++. You can put a web engine on the embedded Linux and write your application as a web application, HTML and JavaScript. Typically at the bottom of the system, though, you have more or less a vanilla kernel. If you get a board support package from a chip vendor, they often have an extensive patch set on top of that kernel, so it's not always possible to run a vanilla kernel. And fundamentally, at the bottom of your user space, pretty much all applications are built on top of the glibc library. And this standard C library gets to be fairly important when we talk about the space between Android and Linux. So just to look into those. On the Android side, you have Bionic. It was developed specifically for Android. It has a very embedded focus. It tries to run on small devices, not use a lot of memory. It's compatible with pretty much all of C++, or C11, sorry, and POSIX. It has some extensions from outside of the standards. For C++, the story is a bit more complicated. It used to be fairly poor. They have added some stuff, but fundamentally, Android is not a platform meant for supporting C++ applications. They just support what they need from C++ in order to get the Java stuff on top and get the Java ecosystem, which is what they really try to push. On the embedded Linux side, or with glibc, glibc is used everywhere. It's compatible with everything. It has a lot of focus on backwards compatibility, on supporting a lot of standards. And it's compatible with pretty much any chip out there. Any chip that runs Linux basically can run glibc, I guess.
One important issue in this space is the fact that if you have an application or a library that builds with glibc and you want to build it with Bionic, you probably are going to be needing source code changes.
Yeah.
So this is not a mix. You can't just flip as you want. And that's going to become an important problem.
Yes. So let's just look at a regular or typical platform diagram for an embedded Linux. You have the kernel at the bottom. You have the glibc C library on top of that. And you also have device drivers, obviously, for your devices. And then you typically pull in whatever components you need to support your application. You can build your system, low-level system utilities using systemd is modern these days. You typically pull in BusyBox to get some shell utilities. You pull in the libraries you need. You have some hardware abstraction to deal with your typically your graphics infrastructure or other stuff. And you basically pull in whatever you need on top. If you're running a C++ application written against Qt, you need to pull in the Qt framework. If you're writing a web application, you probably need some kind of web engine like Chromium. But yeah, it typically looks something like that. On the Android side, however, what you get is basically, this is what Android gives you. You get the Linux kernel with the Android features enabled at the bottom. Typically that comes from your chip vendor, not directly from Google. But then you have at the bottom of your space, you have the Bionic C library. You have the same device drivers. But then all your system utilities, all your libraries is built on top of Bionic. You get the Android set of system utilities like ADB for debugging, Toolbox instead of BusyBox, Android's own init system. And then on top of the drivers and low-level libraries, you get services that Android provide in order to support all the app ecosystem on top. So you have services for integrating with graphics, Surface Flinger. You have Audio Flinger for dealing with audio output and input. And then you have all the Java stuff on top. You have the Android runtime, previously known as Dalvik. Now they use something they just call Android runtime, ART. There's an application framework under your Java apps, and then the Java apps on top. And typically in this space, your application would be written as some sort of Java app. You might want to do some lower-level C or C++ to support custom hardware, for example. But typically, you would then write a Java native interface on top of that to support your main application logic in Java. Now, let's say that your application is heavily C, C++. You don't want to rewrite it into Java. And you can now take your Android and chop away the head, the Java bits. Basically, you can chop away all the Java apps that come with Android. You can chop away the Java application framework, the whole Java runtime, and some of the services that you might not need. So what you're left with is, it sort of looks like an embedded Linux because it's fairly low level, fairly bare bones. But this is still very much Android because it's all based on Bionic. All the system utilities and libraries are still from Android. They're still built against Bionic. And your application, if you want to ship it on this system, you still need to port it to Bionic. And that goes for your third-party dependencies as well. So if that is not easy, and we'll get into some details why that might not be easy, you might want to go a step further away from Android to this thing. So here, we basically pull in glibc on the right side, and now we build our libraries and system utilities on top of glibc instead. And now you can use the regular embedded Linux system utilities that you might be used to beforehand, systemd, busybox, so on. And most importantly, your application and its dependencies, you can now keep those written against glibc for the most part. Because over here on the left side, you still have Bionic also available on the same system in order to support the stuff, some Android stuff. Typically, the reason why you need an Android BSP, it might be the only thing you get from your chip vendor, but also it typically comes with binary-only graphics drivers. Those drivers are already built against Bionic, so you can't just chop Bionic away from the system because those graphics drivers depend on them. So we keep this part over here with Android running. Now, your application, in order to get stuff on screen and integrate with those graphic stuff, it actually needs to talk to those parts. And we will go into some alternatives for actually bridging that gap between a glibc application and having to talk to some Bionic parts. There are a couple of alternatives, and we'll get into those. First, though, basically, the 4 different diagrams I talked about now, you can sort of structure them into this fairly simple space where you have full stack Android on the far left, and you have embedded Linux on the far right. Then the yellow column is basically full stack Android, but you chop away the Java parts. Everything is still Bionic, so we call that headless Bionic. Then you can move one step further towards the embedded Linux by replacing most of your system software with glibc and components built on top of that.
Yeah, so first of all, before you can choose really what kind of architecture you want to have, you also have to think about what kind of device you're making, because that will give a lot of the solution space that you're dealing with. And we're going to talk a lot about composition to screen and these alternatives, but it's also important to talk about that this generally goes for any kind of hardware integration you have. So if you need to be dealing with Bionic-based libraries from your BSP, this same kinds of solutions can be used for anything. So we're going to talk about composition and talk about the screen and displays, but it basically goes for other things like camera or any kind of things where you really don't have a choice. So we're going to talk about 3 classes of display integration into a device. You could have a traditional IoT type embedded Linux thing with no screen, with no display, which is it's the simplest type of device in this space. Then you have a single full screen app, very common in embedded Linux. If you do have a screen that you don't support third-party apps, you just have your one full screen, often OpenGL thing that is. And it doesn't. And then the good thing about that, you don't really need composition. You are the entire screen. Then you move into more of a true consumer type device with multiple apps. So we're going to split up this the columns that you saw previously with these types of devices as the rows, because you will see different kinds of solutions and different kinds of products in them. So first of all, you have this no display, and it has 2 advantages when it comes to how complex your solution has to be, with regards to it doesn't need any graphics integrations and you don't need any composition. So we're going to be focusing a lot on this green column in my talk right now, and then later on Johan will talk more about the yellow column. But the good thing about this upper part here with no display and then headless glibc is you're basically pretty much in a normal embedded Linux. You're not dealing with much Bionic at all. You've been able to chop away pretty much all of Android. You're basically left with the Linux kernel. It's a relatively familiar space to be.
And an example of a type of device that you see in that space, we went looking for Android-based devices that don't have displays, but typically nobody makes them. Android is very display-focused.
Or we wouldn't know.
We wouldn't know because it's not typical that a device manufacturer focus on what kind of underlying platform they run on. But in the embedded Linux space, you have a lot of devices in this space. Pretty much any IoT device that don't have a display. Your typical Linux router or home router typically runs some version of OpenWRT these days, or something similar to it based on embedded Linux.
Okay, and then you come to more of a regular, normal embedded Linux device with a screen, and then you have that full screen app, and you generally can use it for all sorts of things, like a video conferencing endpoint or digital signage. But what you need here now, you need graphics integration, so you need to deal with some Bionic parts, but you still don't need any complex composition. You can still have your full screen window. So when you're in this headless glibc world, now you have to start dealing with some parts of Android. So you need some way of bridging the glibc to Bionic world. And here there are two general solutions. We'll look into them, but one is libhybris, which we mentioned here.
Also, we should just mention that if you're over in the full stack Android space here, then you typically just replace the Android home screen or launcher application with your own application. It gets full control of the screen, and you can basically do whatever you want. On the embedded Linux side, you pretty much write your application on top, either directly talking to the Linux frame buffer or some abstraction on top of that, typically an OpenGL thing. But yeah. In this space with single apps, there are some products. Again, it's not usual for products to advertise what kind of underlying platform they use, but we have personal experience with some of these, so we could fill in some of the blanks. Some Googling suggests that what runs in the Tesla car on the Tesla car OS is also an embedded Linux, running basically simply just the Tesla app.
Yeah, and then you come to a regular consumer device, phone, tablet, smart TV type of thing, where you have multiple apps. There are multiple processes, they produce multiple frames, and all of these frames will have to be composed into one finished picture for the screen. So basically, you're going to need two important things. You need the App Store, some kind of App Store. It could be your own or Google Play or something else. And you need complex composition. So now you need some way to compose a more complex frame. Okay, so we just touched on the left column, but I'll just go a little bit through how you could do this kind of scaling here. So down here in the bottom left, you will see more of a regular Android type device with the Google Play Store or possibly your own store. And it's what people think of when they think of a regular Android device. You're in the bottom left corner here. When you come to the full screen home screen app thing, then generally your users won't be able to tell that you're Android. You won't advertise that you're Android, so you might have a lot of devices being shipped in this fashion, but you won't necessarily know that it's Android underneath. And then even more hidden would be the top one, where you could have an Android app type service, which is more of a background process running. And so you could still imagine making a full stack Android device with no screen and still writing your application in Java, but being a background service kind of thing. On the bottom here, you'll have the two concerns that we talked about, having some kind of app store, but also being able to do complex composition. And for these two central ones, they're very similar. They need some way to communicate with the Android parts for composition. And the low-level Android API for composition is called Hardware Composer. It basically has several surfaces that composes together, and then you have Surface Flinger, which is a service running on top of Hardware Composer, which does some of this for composing different kinds of apps. So it's for more complex composition. And again, you will need some way of bridging the glibc bionic gap there. And on the far right there, that's a traditional embedded Linux device with an X server or Wayland or something like that.
And in this bottom space with multiple apps, on the left-hand side, of course, this is your regular Android phone or tablet, but you also have devices like the Kindle Fire, which runs a full-stack Android. Doesn't necessarily look like a full-stack Android because it doesn't come with a Google Play Store, it comes with Amazon's own store. In the headless bionic case, there aren't really any players these days. The Qt company had a project called Boot2Qt, which was a solution for helping developers getting a Qt stack up and running on an Android BSP to help them develop Qt-based products with Android at the bottom. In the headless glibc space, we actually have a couple of players, most notably the Jolla company from Finland with the Sailfish OS. Canonical had Ubuntu Touch, but that's now inactive as far as we know. And over in the embedded Linux space, you have a few smart TV players like Samsung and LG that do their own multiple apps running on top of a Linux architecture.
One thing that's interesting to note is some open projects have used porting of these types of TV OSs to this type of space. So you have seen several cases of people doing ports of those kinds of solutions to this green box. Okay. So then we're going to talk about composition. And like I said before, composition is just an example of hardware integration where you need to talk to a bionic library. So basically, you need to get your pixels on screen somehow. You have the just one full screen window, or you have multiple windows that you have to compose into one window. But basically, you will have to have some way of doing your composition to screen. So then you have to deal with the hardware composer, either directly or indirectly. What we have seen in the different kinds of solutions that projects have used is that, for example, in the Ubuntu Touch, they started off using Surface Flinger and then ended up not using Surface Flinger. Also in the Sailfish OS, they had Surface Flinger and stopped using Surface Flinger, ended up going straight on the hardware composer. And the hardware composer is a standardized Android API, so it is it's very conformant across different devices. Basically, you will give it a set of surfaces. You have some mechanisms for synchronization and composition where you place them on the screen, and Surface Flinger will then a hardware composer will then compose the final frame out of this and push it to the screen for you. So then we come into this bridging the gap thing. So we're going to talk a little bit about libhybris, very touching on top of it. It could be a whole separate talk, actually. So libhybris is an interesting project. It was started by Karsten Munk, working on the Mir project for Sailfish OS. And he was trying to solve this problem of being able to load bionic graphics drivers in a glibc-based application. And the problem is that, how do you do that? You can't runtime link in bionic libraries into a glibc application. It just doesn't work. And that's what libhybris is. And so you can ask me after the talk how it kind of works, but basically it does actually link in bionic libraries into a glibc application. Okay, so basically you end up with something that looks like this. So this green box, it sort of signifies your glibc application, and the yellow stuff is bionic stuff that you have linked into your address space. So they are in your memory. And you can also see here that you now have 2 libcs in your own memory. So it is a very interesting, it was kind of a crazy idea, but he actually made it work. And it works. It's kind of scary, and the code is kind of freaky. And you have to like linkers and loaders. I recommend reading a book before you go into the code. But it's a very interesting project. But then you have like, okay, it feels kind of maybe a little bit crazy, and so you're thinking, okay, can we do this in a different way? And yes, there have been solutions in doing it in a different way. And basically, the idea is then you place the Bionic library in its own process, in its own Bionic process, and you have your application in your glibc process, and then you do IPC between them. And this, for GPUs, this is the solution that runs in Chromium today. So all of your Chromium-based browsers do this. They have their GPU process. You can see it if you look at your processes on any platform. You will have a GPU process. And all of the other processes will submit OpenGL commands through pipes to this process, and that's how it works. And so this you can do for any type of library. So we have also done this, and here you will have your pure Bionic library, and you have your pure Bionic process here with Bionic libraries, and then you have your pure glibc process here with glibc-based libraries, and then having some sort of IPC between them. So that is also a viable solution. It's not necessarily very easy to do the serialization here, but you can look at, for example, projects like Chromium to look at how that can be done. Okay, so Chromium. It has been done many times that you will make an embedded device where your UI is basically a web app. It's a full-screen web app, and that's what you do. And that is also a possibility for making an embedded device. You need some sort of composition, and the nice thing about a browser is that it has built-in composition. So basically, you have the same idea. You have a single full-screen web app and this type of electron model, like you will see, like Visual Studio Code or what's it called? This Sublime, which are basically web apps that are running on an underlying Chromium. So it is a one full-screen web app, really. So most of you are actually running this on your desktop machines. But then you have more of a traditional browser model where you have multiple apps, or in the typical browser idea, you have multiple tabs. But how you actually compose them together, that's your choice. But here you actually have built-in composition and multiple processes, multiple instances of web apps, and so you have the possibility of having more of a multi-app design. Yeah, so I touched on it, and basically I have a talk on the Linux sandboxing, and in the Linux sandboxing talk for NDC, which is on video, you can go look and see a little bit about how the process architecture for Linux in Chromium is. But basically, you have your own GPU process, and the composition is done there.
So, going over to the lessons learned. We have talked a lot about what is possible from a technical point of view until now, but even if it's all possible, it's not necessarily smart, especially from the perspective of actually bringing up the project and maintaining it over the long term. So if you start with an existing code base coming into this space, you need to consider, should you port your application to Java and run it on top of a full-stack Android? Is that even viable? Or should you port it just from glibc to Bionic to, let's assume that you have a sizable C or C++ code base, bring that over to Bionic, either to run in a full-stack Android environment or on top of this yellow headless Bionic platform that we suggested. Still, you probably need to rewrite to some Android APIs to integrate with the system. What other APIs do you use? Are those APIs available on Android? And even if they are available, does Android already use them and you need to resolve conflicts between various users? And then we come to the big elephant in the room, basically, third-party dependencies. If you have a project of any size, you typically have third-party dependencies. Are those available in Android? Do you need to port them to Bionic? Do you really want to port third-party software to Bionic? Even if you do that port will upstream accept your patches. Some projects are happy to accept patches to port their project to Android or Bionic. Other projects simply just refuse them because they're not interested. So at this point, if you have these kind of third-party dependencies, you really, really need to look hard at them. Can you remove them? Can you replace them with alternative dependencies that already are available in the Android space? And if not, this is something that potentially should push you towards a more glibc-based platform.
And also, you have to also think about, you might be able to handle all your existing dependencies, but suddenly tomorrow somebody will come up with a new dependency, and so you have to have, this is a dangerous space to be. Like I joked with Johan yesterday, it's like a one-way street dead end. I mean, you can drive down, but it's very hard to get out.
Yeah. Yeah. So some general notes about bring up and maintenance. Some lessons we learned here. Bring up is generally easier if you do reuse the BSP that you get from your chip vendor, and you use standard hardware that's already supported by that BSP. If you add a lot of custom hardware, you will typically also need to do a corresponding support work inside the board support package to support that hardware. And those basically become patches that you will have to maintain for the life of your project to keep those working. We would advise, as far as possible, to keep your changes out of the board support package, either writing them on top of the Android APIs. The Android APIs are backwards compatible, versioned, and all that, so you're fairly safe if you can stay on top of those APIs. If that's not possible, try to push them below the BSP into kernel drivers or into the device tree in the kernel, because that also avoids you having patches in the BSP itself. But you will have patches typically. And how you maintain those patches becomes really important for how easy, how achievable it is to maintain your project long term. As I said, avoid patches when you can. Minimize the changes to the board support package itself. Android does have a fair amount of mechanisms for decoupling or isolating your changes from the guts of Android. So if you can put your code into a separate directory instead of patching on the Android files directly, do use those mechanisms. For the patches that you do need to keep, please come up with some scheme for maintaining them, a common scheme that basically you're going to have a lot of patches across a lot of different repos, but use the same scheme for dealing with patches everywhere, so that if a developer has a patch in one tree and needs to write a different patch in a different tree, they still use the same commands, they still use the same workflow, because if you start coming up with different workflows for different repos, it just gets into chaos. You want to be able to enumerate your current patch set, basically to have an overview of, okay, what are the patches we currently have in this part of the code. When you take in a new release from upstream, you want to refresh that patch series, basically rebase it on top of a new release, so that you can remove patches that are no longer necessary, and so that your patches stay current with the development of upstream. Because this is where you want to avoid going. If you basically start accumulating patches, you don't have an overview of that, your code base starts diverging from the upstream. Once the upstream moves on and comes with new releases, you will find it harder and harder to integrate those new releases into your code base. And you basically diverge from your upstream. Do plan for updates to your code base. Android typically comes out with a new version every year. If you're making a device that you want to have a long life in the market, you need to keep up to date with those patches, both because users will expect features, but especially because of security fixes. Third-party dependencies, they have varying update schedules, but do have strict policies for dealing with security patches, especially OpenSSL, for example. If you use Chromium on your device, they typically come out with a new release every month. And Chromium is a huge project in itself, so it's not trivial to follow that. Do expect to spend some effort there. And worst case, your chip vendor might go away. They might decide that they don't want to make SOCs anymore, or you might find that you need to switch to a different SOC down the line.
Or they may go out of business.
Yeah, basically that means changing out your whole board support package for a different one. They're both Android, so they're both similar, but still there are a lot of vendor-specific patches in the different BSPs. So if you actually need to switch to a different BSP, expect a fair amount of work. Basically, not a complete rewrite, but a lot of work going to
But the more disciplined you've been in your patch handling before, it's going to help you in this situation.
When you get into these situations, this is where it's really, really worth having a good overview of what are your patches and having them be current with the upstream releases so that you're as close to upstream as you can manage to be. Because otherwise, you can get into basically the nightmare scenario where you have too many patches. You can't update the Android version because there's just too much of a difference. You can't update third-party libraries. You have too many patches on them. You have basically forked the third-party dependencies in order to support it for your application.
And especially you have to notice that the moment you start patching your libraries for Bionic to build them on Bionic, you are ending up in a position where you're practically forking these projects.
Yeah.
And now suddenly you have, instead of having only like a few projects you're taking care of, you're suddenly taking care of a whole bunch of third-party projects as well, which can be very difficult.
Yeah. And worst case, your security pipeline is clogged because you find you cannot apply security patches from upstream because they don't apply to your code anymore. You have diverged too much. And worst case, your whole project stalls basically because there's just too much to keep track of. So, time to wrap up, get to some conclusion here. So in short, if you stay on the left side with a Bionic-based system, your code, your third-party dependencies must build against Bionic. If you're starting from scratch, you don't have an existing code base, that is probably not a big problem.
Then you just stay in this column.
Yeah, if you can stay on full stack Android, and that's not a problem for you.
And stay in projects using third-party dependencies that support Android. Just stay here.
On the right side, your code and your third-party dependencies are built against glibc. Again, if you venture into this green column, you will need some integration with Bionic, and there are, as we told you, there are solutions here. They are not necessarily easy, but they might be preferable to actually porting your existing application and its dependencies to Bionic.
I think you would say that they are, because the problem is you'll end up here, you have to have very few third-party dependencies before this column makes it worth it, because it amounts to a lot of risk. You might get it to work right now, but it's really, really hard to maintain in the long run, and it could end up with you just not being able to do it anymore. So it's very risky being in this column. So I would say moving over here is a big risk-reducing factor. So in the very short term, or in as short we can make it, basically stay towards the edges if you can. Those are the green columns, the full stack Android and the embedded Linux. That's where you'll have. That's where most other players are. That's where you'll be able to find most support online. And it's sort of the common case. If you venture into the middle, we would say probably prefer a glibc-based platform. Of course, there are a lot of different factors to consider and balance here, but typically, if you try to make something on top of Headless Bionic and you have dependencies, having to maintain those dependencies for the future is... There are no products here.
Yeah, there aren't any other players.
There aren't any players in this column anymore. Like there was a bunch of people tried this column. Nobody's in this column anymore. So if you go into this column, you're on your own.
Yeah. And maybe the most important point: plan for your maintenance. Plan for your long-term maintenance. Have a good plan for dealing with patches. Stick to it. Discipline is important here. Because if you lose track of your patches, if you start having patches all over the place and you don't really know and keep track of your differences with regards to your upstream, you're going to have so much more pain in the future.
And the reason why we're pointing this out is that when you're starting to make these decisions, some paths will seem very tempting in the moment because they seem like, oh, but it's much easier if I go this way. But you have to remember that you might have no way out that way. So you think about before you start, what kind of device am I making? How can I maintain it? How am I going to get my patches in? How am I going to get my patches in 3 years? You have to think about that because that's going to make the decision on where you want to place yourself.
So yeah, at this point we actually have time for questions.
Yes. So, come on, questions. We made lots of mistakes. Some of them we can talk about, some we can't. Yes?
Are there any comments, like you talked about this, I guess it's a daemon that can do the OpenGL stuff for you?
Yeah.
I mean, is that something that you can reuse? Is there an open source product project out there that's running that, or do you have to do that yourself?
Okay, so what happened? What happened in the end was that Yola made the libhybrids came out of the Mir project for Yola for the Selfish OS, and there they made a C-like interface so you could DL open these libraries. But what they ended up with doing is they made sort of like a composition server, which was not Wayland based, but it was based on the Mir, which that whole project has now been abandoned. But what you saw that was in the Ubuntu Touch, but in the but in the Selfish OS they based it on Wayland, and so they made a composition type server which was Wayland based, and you can see, for example, in the Qt project you have Qt Wayland, which kind of does that. So you can make a Qt Wayland compositor process where you can have Wayland processes that as clients to this server, and I think that kind of architecture is probably the best.
I guess you could also look at Chromium and how they basically transfer frames and graphics data from a render process to the compositor.
So the alternative is basically having something like in Chromium where you have basically a GPU process which takes GPU commands over a pipe, and then the entire thing is handled in the central location. But there isn't really like a general open source solution for this space yet. Most people have sort of kind of made their own, but the architectures are very similar.
Yeah, I don't think there is a small project you can go and find that just do the OpenGL forwarding across a process boundary. I don't think there is a project exactly for that and only that.
No, but you can. There's a bunch of projects you can look at to try to see if you can use. Yeah.
There was a question down there.
How does your development environment look like upon testing emulators and such?
Wow, that's a big one.
That's one of the things that we talked about yesterday. We didn't talk about now, but that is also one of the good reasons why, if you're traditionally in the embedded Linux column, right? This is where you've been the entire time. All of your infrastructure, your testing infrastructure, your installation software, your monitoring software, all sorts of things have a standard interface, right? That they're used to talking to. If you suddenly end up here, there's like, not only do you have to rewrite your application, but you might have to rewrite all sorts of other toolings around it, right? So in that case, this is a much better column because it looks and behaves like a normal embedded Linux. From the platform side, of course, it's not. There's like stuff here, but you can make this look from testing perspective, from development perspective, to act and behave like a normal embedded Linux device.
Yeah. Traditionally, where we came from in our experience, we were basically over here, and then we started looking at, okay, maybe we should, or we're getting an Android board support package from our vendor. Do we start working over here? And what we found is that basically Android gives you everything, and by that I mean everything. It gives you a whole repo structure, its own build system, its own test infrastructure. You basically have to rewrite your whole application to fit inside Android. It's not like you fit Android into your system. You have to fit into Android system.
Yeah. And it's my worth saying that we've made stuff in almost all of these boxes. So it doesn't. It's like we have like a big red here, but it doesn't mean that we didn't do that. Okay. Anybody? Yes.
I just not looking for an endorsement or bad nothing, but in terms of vendors, do you have like a favorite if I wanted a general purpose support?
System on chip vendors. I have colleagues that could tell you much more about that. I don't have a personal favorite. What I would say is focus on vendors that really try to upstream their patches both to the kernel and to Android when they can. For the long term, if you're shipping a device and you're supporting that for many years down the road, you don't want to get stuck into a space where you are dependent on a huge patch set on the kernel or a huge patch set on Android from your vendor, because your vendor might go away, and then you're stuck with, oh, we can't upgrade our kernel because we have to use, say, Texas Instruments' kernel patches, and they're not doing those for new kernel versions. So we're stuck on this really old kernel. So try to find...
Texas Instrument was just like an example.
Yeah.
It's like it wasn't, yeah.
So like when you're starting a new project and management is looking at what kind of chip you're looking at, like there are so many other factors that are probably deemed more important than what I'm saying here. But really, if you have the choice, find a vendor that is good at upstreaming patches, has and hence has as small a patch set as possible. And that works with the open source community instead of against it.
And again, it's one of the reasons why this space here is a problem, is because your graphics driver is probably a binary blob that you got from your vendor, right? So if you, for some magic reason, manage to get an open source, OpenGL libraries that you can compile yourself, I mean, seriously, that is like a big advantage in this space.
If you can build your graphics driver on top of glibc, then you don't need any of the Bionic integration at all, and you can stay over here. So all of this is basically about having to deal with a world that is very not ideal, at least not from sort of an open source perspective where you have access to all the source.
But making it work so you can still ship your products.
Yeah.
Yeah. Anybody else? Sure?
Okay.
Okay, next slide. Because I have swag back here, so please just take t-shirts, everything, and then we want like the green ones, right? So just you have to give us the green ones. Yeah. But please take everything because I don't want to take it home.
Thank you very much.